Hi folks. Doing good this morning? Let's start. Let's do some quick questions. Let's back your book, chapter 2. I don't think we've done any of these, have we? All right about that? Alright, so proton and electron are in a constant electric field created by oppositely charged plates. You release the proton from the positive side and the electron from the negative side. Which feels the larger force? Does the proton or the electron feel the larger force? Or do they feel the same force, or there is no force, or they feel the same magnitude force but the opposite direction? Which is it? Which feels the larger electric force? Proton, electron, the same force, there is no force, or same magnitude but opposite direction. Alright. Remember to think back, this goes back to our chapter 1 with electric fields and forces and all that business. So think about what is the charge on our electron and our proton, and then they're in this electric field. Sort of forget about the potentials for now. We're not terribly concerned about that. But what is the force that these charges feel? I'll stop at 1, say 118. 118. All right, good. E is the right answer. Let me show you. So we know with our electric field that the force due to an electric field is equal to Q times the electric field. In this case, we have a constant electric field, so both the electron and the proton feel the same electric field. And so also we know that an electron and a proton have the same charge, or rather, an electron is just the negative of what the proton's charge is. They both have that fundamental unit of charge E, that 1.6 times 10 to the minus 19. So both of them will feel the same force, except the electron will feel a force in that direction, and the proton will feel a force in that direction. The electron feels a force opposite the direction of the electric field. The proton feels a force in the same direction as the electric field. So they feel the same magnitude force, but just the opposite direction. So same situation, proton and electron. You release the proton from the positive side over here, and you release an electron from the negative side over here. Which has the larger acceleration? Put it down. Which feels the larger acceleration? We had a very similar question to this in chapter 1. I'll stop at 42. 42. Okay, good. B has the larger acceleration. They both feel the same force. Why does the electron feel a larger acceleration? Mass is a lot smaller. By like a factor of 10,000. The proton's mass, isn't that right? 10 to the minus 27, 10 to the minus 31. Yeah, about 10,000 times smaller than the proton. So it feels an acceleration that's going to be 10,000 times bigger. Okay, same situation. Proton and electron released in this electric field in between these two plates. When they strike the opposite plate, which one will have more kinetic energy? The electron or the proton? Now we already know the electron is going to go on a whole heck of a lot faster because it accelerates at a faster rate. But what does that tell you about the kinetic energy of the proton and electron? Proton has more, electron has more, same kinetic energy, no change in kinetic energy, or same kinetic energy but opposite signs. I want to remind you of what potential is. Okay, here we have two charges that are moving across a certain potential. What is potential? Right, we have forces, we have fields, which are forces per unit charge, and then we have potential. What is that? Basic idea. What is potential? It's something per unit charge. What is it? No. All right, basic idea behind potential. Thank you, Dean. But it's energy per unit charge. Right? Field is a force per unit charge. Potential is energy per unit charge. That's the basic fundamental idea behind potential. So if our potential is energy per unit charge, how are these energies different for the electron and the proton? All right, I'll stop at 155. 155. C is the right answer here. They're going to both acquire the same energy. The reason they're going to both acquire the same energy is because both of these go across the same potential difference. So delta V is the same for the electron and the proton. It's the same for both of those. And since potential, my delta V, is going to be my change in energy over the unit charge, whatever that charge is, because the electron and the proton have the same charge. They both have the same charge. They both are going across the same potential difference. They're both going to experience the same change in energy. Okay? We used this idea last time in order to calculate the velocity of a particle that's in a potential field, in a field that changes potential, in order to find its kinetic energy and hence its velocity. So here, because these have the same charge, they have the same change in potential, they're also going to have the same energy. Because potential is what? It's what per unit charge? Energy. Potential is energy per unit charge. Okay, we'll get into this. Talked about how you can isolate these particles, charged particles, at a potential well. Y'all did this in lab with the charges and fields and the electric field hockey. It's there if you want to go play with it some more. Let's see. Okay, so we're going to move on now to electric potential due to a point charge. Okay, so the electric potential due to a point charge is given by kq over r. I'll just sort of give you a recap of what we've had. We've had the force is kqq over r squared. And then we had electric field, remember, which is force per unit charge. So we lose one of those q's, is going to be kq over r squared. And now we have potential, which is energy per unit charge, kq over r. So notice they all look very similar, but you sort of have to learn to distinguish them in your mind. We're also going to set a reference that when r is equal to infinity, when you go really, really far away from a charge, the potential at that point is going to be equal to 0. So, for example, here I have a charge plus q. I have some point that is a distance r. What this tells me that at this point, my potential is kq over r. That tells me that at this point in space, I have an energy per unit charge that's equal to this kq over r. And I have an energy per unit charge that's equal to that. And so if I put a charge there, I could figure out the energy, or the potential energy of that charge. I have an energy per charge equal to V at that point, which happens to have the value of kq over r. We'll show you how we get to that in just a second. So if I put a charge at that point, then I can calculate the energy, the potential energy, which is going to be q times V. based on this basic definition or this basic understanding of what potential is. The way we calculate this potential at this point is going to be this kq over r. This is the potential due to a point charge. If I make that r really, really big, so in this inverse relationship, if I let r go to a very, very large value, then that's going to mean that the potential goes to 0. You should have seen those limits before in calculus, and we've seen them indeed here. That when I let r go to a really big number, that v goes to 0. This is really derived through calculus, this idea, but we can do a sort of ad hoc derivation, and it's not completely wrong, but it looks like this, that my delta v is equal to E times delta x, where that's my electric field. We've seen this before. We saw this earlier when we were talking about energy and potential. And so I can say then that E is kq over r squared. I'm going to let my delta x be r, just sort of taking those units, and then I'm left with this kq over r. All right? We'll do some more derivations for the potential due to irregularly shaped objects in just a bit, but just for now, know that the potential due to a point charge, that's equal to kq over r. The electric potential, y'all ready for this? Because this will make your life a lot easier knowing that this is true. The electric potential is a scalar quantity. All right, because all that business that we had to do in the first chapter with the vectors and all that jazz, we're not having to do any of that with potentials. And so I think you'll find that potentials are a lot easier to deal with simply because they're scalar quantities. You don't have to worry about all the trig and all the geometry and all that jazz where you're adding up vectors. In fact, I don't think we do that again. Well, we see some vector, like three-dimensional vectors in chapter 5. But we're pretty much done with vectors for this class. All right, so the electric potential is a scalar quantity. So the potential of multiple charges adds just arithmetically, not like vectors. So for example, we'll do an example here in just a second, but if I have, say, two charges, say a positive charge here and a positive charge here, we'll call this Q1 and I'll call this Q2. And let's say that I have a point over here in space and I want to know what the potential is. Now, the potential due to this charge is going to be, if this distance is R1, that potential is going to be KQ1 over R1. The potential due to this charge, if this distance is R2, it's going to be KQ2 over R2. And if I want to know the total potential, I just add those two up. If I want to know the total potential at this point, the total energy per unit charge at that point, then I just add those up like numbers. As we'll see, also, that if I have a negative charge, like let's say instead of this being positive, that this is negative, then we'll find that this value is also going to be negative. All right. Point there is that when calculating V, or the potential, include the charge signs. Whether it's positive or negative. That's not something we've done before because we've accounted for the sign of the charge in the, when we write the vectors, when we draw the vectors, we ask ourselves, well, what is the direction of this force, or what is the direction of this electric field due to this charge, be it positive or negative. But here, we're just going to include that sign when we calculate the potential. So a negative charge will have a negative potential, a positive charge will have a positive potential. All right, let's try this. Oh, so one result of this is that if I have a positive charge here and an equal but opposite negative charge here, and I take a point that's equidistant between these two charges, meaning R1 is equal to R2, what is going to be my potential at that point? It's going to be 0. So because I include this sign, I can have negative potential or positive potential. I can have points in space where I have no potential at all, where there is no energy per unit charge. Let's try this little quick test. Here I have these configuration of charges, and I want to know what is true at that point P. What is the electric field, and what is the potential? So to find the electric field, let me remind you, you put a positive test charge and you ask yourself what is the direction of the force due to these individual charges, and then you have to add those up like vectors. So I'm asking the question here is, as the electric field at point P, is it positive, negative, or 0? Or actually, is it 0 or is it not 0? And then also, the potential at point P, is it 0 or not 0? To find the electric field, you want to actually draw out the vectors. It might not be immediately obvious. It might be obvious to you, but it might not. I would draw out the vectors at that point P. And then think about the potential, and what is the potential at that point P? Stop at 130, 130. Just guess if you're not sure. Okay, I think that is right, actually. Let's see. First of all, we can look at the potential, and because the point P is equidistant from all the charges, and I have positive charges, and I have 2 positive charges and 2 negative charges, I can say that the potential is going to be 0. Right, so the potential due to this charge is going to be negative, and it's going to cancel out with the potential due to that charge. Likewise, the potential due to this charge is positive. It'll cancel out due to that charge. So the potential will be 0, because I'll have these 4 numbers, 2 which will be positive, 2 which will be negative, and they'll just add up equal to 0. Now, for the field, it's a little more complicated, though you might have just been able to look at this and tell that the electric field due to this charge will be in that direction. Remember, I let a positive particle be there. I asked myself, what is the direction of the force? The electric field due to this particle will be in that direction. It'll be repelled. The electric field due to this particle will be in that direction, and the electric field due to this particle will be in that direction. And so that net electric field will equal to 0 because all those vectors are going to cancel out. It doesn't have to be that way. In fact, we'll see some other problems where it's not that way, where if you move your charges around, then the electric field doesn't have to be in that direction. Okay, let's do the, you'll probably see a problem on the next test, probably, maybe, see a problem where you have to find the potential due to a collection of point charges, and then also you'll likely see where you have to find the potential due to a shape that's charged. But let's do the point charges first. I think you'll find this is pretty simple. If I want to know the potential at point P, I have these 3 charges, Q1, Q2, Q3 are all 3 nanocoulombs. Then my potential is just going to be V1 plus V2 plus V3. That's really just adding them up. I say K times Q1 over 1 meter. Actually, I'm going to go and put in some numbers here. Skip that step. I'm going to say 9 times 10 to the 9th. That's my K value. Q is 3 nanocoulombs divided by R, which is 1 meter, plus 9 times 10 to the 9th, 3 times 10 to the minus 9. You don't have to write out each of these because you'll see that they're all the same. because they're all the same distance. You could just multiply by 3, right? Divide by 1, I get some cancellations here, 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 and here. And so that's 3 times 27. It's about 60, 81 volts. 81 volts. So collection of point charges, that's sort of the simplest. Have 2 or 3 point charges and find the potential due to those. You can see slightly more complicated. So say, for example, I gave you a problem like this where I give you charges that are on a triangle. Say I give you a charge that's here and here. Oops. Give you these charges. Let's say that this is, we'll call this a 3, 4, 5 triangle. This would be 4 nanocoulombs. We'll call this 5 nanocoulombs. And I want to know what is the potential here at this point. So I don't need a charge here, right? Like when you're finding the forces, I would have to have a charge here to find the force. But I'm really just looking for what is the energy per charge at this point in space. And then that'll tell us something about if I put a charge there, what is the potential energy, the actual energy of that charge in that configuration. But if I were to find the potential here, I'll give you a minute to find that potential at that point. The numbers work out pretty easy. I got the potential. 81? No, not 81, is it? I don't think. Right, it's 18. It's not multiplying them. You add them up. Yeah, so good point. You'll probably never found the potential due to point charges, so it's good to get this a little bit of practice. So I do KQ over R plus KQ over R. Do this one first. 4 times 10 to the minus 9. Excuse me, 9 times 10 to the 9th. K. 4 times 10 to the minus 9. That's in coulombs. Nano is 10 to the minus 9 divided by 4 meters plus 9 times 10 to the 9. 5 times 10 to the minus 9 divided by 5 meters. Cancels, 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 cancels. So I'm just left with 9 plus 9. Just add them up. If they were negative, like let's say the 5 nanocoulomb charge was negative, then what would the potential be? It would be 0, because I would have a negative 9. So for example, if this were negative, that would mean this would be negative, and I would have a negative there, and it would equal to 0 volts. Okay, those aren't terribly complicated. Like I said, there's not really a whole lot of steps. As you can see, a 5 or 10 point question on the test, probably going to be paired up with something else that we'll do soon on potential energy. But hopefully that's a gimme question on the test. As you know, when you're in a test, really no question is a gimme question because, you know, you sort of got the fog of an exam on your mind. Okay? But practice this. There's some in the homework. Make sure that you can do that where you find the potential of a configuration of charges. It could be 2 charges. It could also be 3 charges. Probably wouldn't be more than that. Let's try this one. I have 2 charges here, plus 2Q, minus 4Q. And the Q value is 2 microcoulombs. So this would be plus 4. This is minus 8 microcoulombs. And I want to know what is the potential up here where the smiley face is. The smiley face isn't a charge, it just represents a point in space. What is the potential at that point? So try that out. Think about some ways that you can make it a little simpler. There are some ways to make it simpler. Think too about how you can rule out answers. Looking good so far. Ask your neighbor if you're not sure. It looks like most of you are sure about it. All right, let's try to wrap up in about 10 seconds. Just guess if you're not sure. Ask your neighbor. You'll probably have it right. Let's stop at 210. 210. Okay, awesome. A is right. Couple of quick ways that you could look at this problem. You could say, well, gosh, I have a plus 2q here and a minus 4q here. So I have, and both of these are the same distance from the point. Now you have to consider the distance, because if they're different distances, they can have different potentials. But in this one, because they're the same distance, and I have more negative charge, then I can really just treat this problem, just get rid of this charge completely, and just say that this charge is minus 2q, or minus 4 microcoulombs. So I'm really just asking for what is the, if I have a minus 4 microcoulomb charge, what is the potential at 1 meter from that charge? You'll see how I did that. I can cancel out part of the problem, because what I have is I'll have V is equal to K times 4 microcoulombs over 1 meter plus K times minus 8 microcoulombs over 1 meter. Okay, so I can just say that, well, I'll just get rid of this and make this a 4 instead of an 8, because it's the same distance. All right? And then I can also say, well, since I have this excess of negative charge, the potential has to be negative, so I can get rid of B and C altogether. And then it's really just a matter of say, well, K is 9 times 10 to the 9th, negative 4 times 10 to the minus 6 divided by 1 meter. And the 9 and the 4 will tell you that it should be 36,000. Alrighty? Good job on that. Let's see, what did 0 say to 8? And then y'all say, I don't know what. Nice belt. You get it now? I get slowly rolling. It's like a wave. It takes a little while. Okay? Okay. All right, let's look at the electric potential of charged objects. We're going to do this derivation. This is a... We're not going to do this as something that you turn in like we did on the last one, but I might require you to do this as a derivation on the test. All right? I'll let you know when we get closer to the test in a couple of weeks, which remember the test is 2 weeks from Friday. It's a pretty simple integral. All right, and it's a nice process. It's a process that you have to do in a lot of other scenarios. So let's say that I have a charged rod. The charged rod is of length L, and I want to know what is the potential at a point, a distance d above the rod. So I want to express the potential in terms of L, d, and a lambda. Do y'all remember what lambda is? We use this when we were doing the derivations for electric field. Lambda is a charge what? Yeah, it's a linear charge density, right? So linear charge density is the charge per unit length. Remember we had lambda, sigma, and rho for linear area and volume density. So lambda is our linear charge density. Our basic process on this is going to be to break this up into little pieces like that, and then at each point we'll say what is the potential due to that part? What is the potential due to that part? What is the potential due to that part? And then just add all of those up. It's an integral, right? That's what we do when we do integrals. We divide it into differential elements, and then we integrate across that entire object, adding up the potential that we want for each one, for each part. We begin with our basic definition of potential, that the potential due to one of those differential elements is going to equal to K dq over R. That just is the potential due to a point charge, but now I'm expressing it in terms of my dq. This is my little differential element dq. The potential due to this charge at this point is going to be K dq over R, where R is going to be a variable that we'll have to express in other terms, because it changes, right? R for this differential element is this distance. For this differential element, it's a different value. So we'll need to express R in terms of variables that will change as I move across from 0 to L. All right? I can further say that dq is equal to lambda dx, where x, you know, will run from 0 to L. Right, this is x equals 0 down here. This is x equal L down here. So I'm expressing my dq in terms of this linear charge density. Remember, lambda has units of coulombs per meter. It tells you how much charge per unit length you have on a one-dimensional line. And so when I multiply lambda times the length of my differential element, that gives me the charge on my differential element. So if I look at my little differential elements, they have a charge dq, and they have a length dx. You with me? Okay. So I define my charge in that way. Now I need to define what is R. So this is going to be R for just a general differential element. How do I define R? What is R? What can I define R in terms of when variables that I'll be able to integrate over? Well, D isn't going to change, right? So I can include D. What else do I need to include in my definition of R? Something that will change as I integrate over that bar. X. So I need to define R in terms of D and X. What is R in terms of D and X from that picture? Right, because this is a right triangle. Right here. So I can define R as the square root of D squared plus X squared, where X, if this is dx, then X is just any point on the line. So X is going to change. I'm going to allow X to go from here all the way out to X equal L. And at each point, as X changes here, it gives me the new value for R. R is also going to change. Initially, R is going to be small. It's going to get bigger and bigger and bigger and bigger as this distance increases, as I integrate over that bar. Okay? So that's r. I've defined dq, and I've defined r. And now I can substitute those in and say that dv is equal to k lambda dx. I just substitute that dq in, divided by r, which is the square root of d squared plus x squared. Okay? So now I'm ready to do my integral. I integrate, remembering that I'm going to integrate from x equals 0 to x equal L, because that will go across this entire bar going to the end. And it will sum up the potential for each of those differential elements. You with me, folks? You should be doing stuff like this sort of in Calculus 1 or 2 if you haven't already. The integral of dv is just v. I can take some things out of this integral here. What can I take out of this integral that doesn't change with x? Which of these variables do not change with x?
K and lambda.
K and lambda. D also doesn't change with x, but it's sort of wrapped up in this, this square root. I can't easily take that out. So I can take k and lambda out very simply. K lambda integral dx over square root of d squared plus x squared. Okay? Now at this point, you want to do this integral. You want to execute it when I'm going from x equals 0 to x equal L. Gosh, I guess you could do that. What do you do that? Integration by parts? I don't know. A good calculus teacher. No? Trig substitution, yes. I've long forgotten that. But if you have an integral like this, like if I give you the derivation, I'll give you a snippet from the integration tables. Y'all used to using integration tables? They let you use them in calculus? You know what an integration table is? An integration table, let me see if I can pull up. I don't think I would have made it through undergraduate without integration tables. Integration table looks like this. All right, it shows you particular solutions to common integrals. So for example, let's look at, see if this one is on here. I don't see it, but let's say that you had, can you see that at all? Sort of. Like here's like the integral of dx over the square root of 1 minus x squared. Okay, and then it gives an arc, it has a solution, it has two solutions. It's an arc sine of x plus c, or minus arc cosine of x plus c, which is an integration constant. So an integration table will give you that solution. I've looked this up. Turns out that the integration table here gives, I pulled this from Schaum's Mathematical Handbook. Really nice book. It has a lot of integration tables. It's a little short paperback. And it also has a bunch of different like geometric formulas, trig identities, all that business. But in Schaum's, it tells me that the integral of du over the square root of u squared plus a squared is equal to the natural log of u plus the square root of u squared plus a squared. And I recognize that this is the same form as this, where I have dx is the square root of d squared plus x squared. Here, what is my u? In my integral up here, what is u? It's x, right? Yeah, be careful because the variables are sort of mixed around. My du here is going to be dx up here, so u is x. So here where it says u squared, that's going to be x squared, and a squared is going to be d squared. A is my constant. U is my variable that changes with the integral as I integrate over. All right, so I can then write this, given the solution is going to be k times lambda times this natural log of u, which is x, plus the square root of x squared plus d squared. Almost there. Now we just have to put in our limits of integration. Go from x equals 0 to x equal L. And so that's going to look like this. K lambda natural log, well, there should be a parentheses here, I'm sorry. Natural log of L plus the square root of L squared plus D squared. And that's it. That is the potential due to a line of charge. All right. Let's see. I'll go ahead and make a little mini integration table, and I'll put it on your equation sheet. So, you got a question?
Would you still have to subtract D? Yeah.
Yeah, you're right about that. Yeah, I would have to subtract the natural log of D. Sorry about that. Let me go back and fix that. So it's going to be minus the natural log of D. You'll follow that because L here, I'm going from x equals 0 to x equal L. This is my final. This is my initial. So I do the natural log of L plus square root of L squared plus D squared minus the natural log of 0 plus the square root of 0 squared plus D squared, which is just the natural log of D. Okay? So I'll give you a little mini integration table that I have 3 or 4 different options to pick from. That'll be similar to this, where you have the integral of du over blah, blah, blah. And I'll put that on your equation sheet, just to show you that sort of mini integration table. Integration tables have hundreds of different integrals to pick from, but I'll just give you 4 or 5. And then you'll have to do this derivation. Not certain that it'll be on the test, but probably will. It's useful to just sort of have this process down, not just for this class, but for other classes too. It's a nice thing to be able to integrate across a regularly shaped object in this way. Okay? Yeah, I did that last time with the fields due to the charge disk. This one is a little bit easier because it's not a vector and because it's not radial. It's not a polar coordinate. Anyway, that's exciting. It's good. Do derivations at 8 o'clock in the morning, right? Yeah, ooh yeah. All right. Let's see. Okay, so the potential at point P, we've already seen this, is KQ1 over R. If I have a charge Q1, it's a distance R. It's going to be KQ1 over R. Now, the work required to bring another charge from Q equal infinity to where that charge is located is going to look like this. It's going to be Q2 times V1. Imagine I have a charge, a positive charge, way over here. What is the potential at this point due to that charge Q1? At this point. I'm way over here at a really far distance away from Q1. What is my potential due to Q1? It's 0 because R goes really, really big, V goes really, really small. It approaches 0. And then as I bring this charge in, it begins to move in this potential field. It begins to feel a greater and greater force due to that charge because I'm moving closer. Or you can think of it as I move closer, the potential due to this charge begins to increase because I'm getting closer to it. Imagine really far away, potential is 0 because R is really big. But as I move this positive charge closer and closer and closer, it begins to feel more and more force, and I have to do more and more work to place it at this point P. So I have to do work in order to take a charge from over there and move it to right here. We want to figure out some way to express that amount of work that is required to move a charge from really far away to some point that's near to a charge. Because when we do that, then we'll be able to figure out what is the potential energy in a configuration of charges. And when y'all get into PChem, that'll be useful because you need to know sort of what is the energy in a configuration of charges, i.e., an atom, to know what is the energy contained in that system. So my change in potential energy for this charge, this imaginary charge that I move, Q2, over here, the potential due to charge 1 is 0. But then I want to move this over here. The potential at this point, due to charge 1, is not 0, right? It's that KQ over R, KQ1 over R. The change in potential energy for charge number 2 is going to be equal to Q2 times V1. Remember, because we have this basic idea that potential is energy per charge, so if I just multiply my charge times my energy per charge, that'll give me energy. What is the potential energy of that system? So that's going to be Q2 times KQ1 over R. So my potential energy then will be, just rewriting this a little bit, KQ1, Q2 over R. And this is in general true, that anytime I have two charges, their potential energy is going to be equal to that value. So here I have plus Q1, they're separated by a distance R. Their potential energy is equal to this value, KQ1, Q2 over R. And as we've been doing, include signs for the charges. And you can think about this, if I go back to this original scenario, if instead of Q1 being positive, let's say I have a negative Q1 here, and then I have this positive charge way over here, what do I have to do to get this negative charge over there? What if I just let the charge go? I'm holding this positive charge. What if I let it go? What it's going to do? It's going to zoom right on over there. It's not going to go to point P. It's going to go straight to Q1. So in order to move this charge over to that point P, it's like a dog on a leash. You know what? Like an unruly dog on a leash. What do you have to do to an unruly dog on a leash? And you got to pull it back. It's like I'm pulling it back and it's pulling me over there. So I have to do negative work because I have an electric force going in that direction. I have to pull back in this direction to hold it back so that it comes over to point P. My dog never pulls on the leash because he's a good dog. But they say actually when you walk a dog that the leash should never go tight. Right? Do you have dogs? Do you walk them? Yeah, you should always have this nice J in the leash. You gotta have a good dog to do that, or a good owner rather. Okay. All right. Let's see, where are we? Okay, so if Q1 and Q2 are both positive, then the potential energy is positive. That comes out just in the equation. And that means that positive work must be done to hold them in place. So, for example, I have to apply a force in order to move my charge in this direction. That's like the two positive charges coming together. I have to force them into place. If Q1 and Q2 are opposite in charge, the potential energy is negative. And that means that negative work must be done to put them into place. Remember, negative work is where the force and the displacement are in opposite directions. And so, for example, like with the dog on a leash, I have a force that's in this direction. I'm sorry. No, the applied force, the displacement is in this direction. I'm trying to move in this direction. But in order to make that happen, I have to apply a force that's opposite that. And so this is a negative work. And hence it has a negative potential energy. Okay? Those are just sort of notations that we'll use, but they'll be important when we get into working out some of the problems. All right, so let's just try this quick one. So if I have these two charges, how much work is required to assemble those charges? I have a plus 2 microcoulomb, minus 3 microcoulomb, separated by 1 meter. Y'all just try it out right now. What is the work required to assemble those two charges? Or what is the potential energy contained in that configuration of charges? And we'll wrap up with this. Try it out on your own. You know, if you get a value. I got a value for it? I think it is. Let's look at the, you have to be careful with your notation. I think it is 0.054. Let's see. So it's 9 times 10 to the 9th. Q1 is plus 2 times 10 to the minus 6. Minus 3 times 10 to the minus 6. And then the distance on the bottom is just 1 meter. Be careful, it's not squared like it is for force. It's just R. Yeah, so that looks like 54. So it's 10 to the 9. It's 10 to the third, 10 to the minus third times 10 to the minus 3. That is 0.054, and it is negative. So negative 0.054 volts. Now, if we have a third charge, and you'll see some in the problem, in the homework like this, and we'll do some as well next time. If I have a third charge, or fourth charge, so let's say I have a Q3 here, it becomes a little more complicated, because you have these two charges that have potential energy, then you also have these two charges that have potential energy, and then you have these two charges that also have potential energy. You have to calculate the potential energy due to each distinct pair of charges. When you have 3 charges, you have 3 distinct pairs. When you have 4 charges, what do you have with 4 charges? You have this pair, you have this pair, you have this pair, you have this pair, then you have that pair, and I think just one more. I think this pair. I think that's it. You have a bunch of different pairs. We'll work a problem like that next time. But let's go and call it a day. Okay, you all have a great day. I'll see you on Friday, I guess. Friday.